Good morning, good afternoon, good evening, wherever you are, and a very warm welcome to this IUSSP training workshop on extracting spatial data on environment for your research. I'm Nico van Imwegen. I'm the Secretary General and Treasurer of the IUSSP, and it's my great pleasure and an honor to welcome you to this workshop on behalf of the Council of the IUSSP. The IUSSP, as you may know, is the Worldwide Association of Population Scientists, and if you're not yet a member, you should definitely consider to join us and join our international network. And if you're a student, please know that student membership is free for 4 years, so another reason to join us. So after this workshop, go to the IUSSP website and find more about membership and about joining IUSSP. In the Union, we have several scientific panels that help us building up our scientific program. And one of those panels is the Early Career Perspectives panel. And we're very happy that one of the members of that panel, Ankit Sikarwar, offered to organize this workshop on spatial data and environment, and to see how you can enrich your research by using that data. And we're very proud that he did so, and we owe him a very big thank you on behalf of the IUSSP Council. So this workshop is one in a series. If you want to have a look at other workshops that we have organized in the past, also go to our IUSSP website and see what we have done. But for now, this afternoon, we will have a very full program. And without further ado, I will give the floor to Ankit, and I'll wish you all a very successful workshop. Ankit, over to you.
Thank you, Nico, for the nice and short opening. So hello and welcome again to the participants with a lot enthusiasm to explore environmental data. And before I introduce myself, let me just thank you all for showing a great interest in this webinar. And let me just show you this very fascinating scene here. And if you can see this, I hope you are able to see this. So we have more than 40 participants from different parts of the world. And let me just share my slides again. Okay, so we are, I would like to request all of you for turning on your cameras for a while so that you all can see each other before seeing the slides, just for a few seconds, and we can turn it off later. So I have myself on and I wave my hands to say you hi. Hello, everyone. It's really nice to see all the faces of, I think we all are environmental scientists first, and it's nice to see you all, and it's my humble request to keep yourself muted during the introductory session as well as during the hands-on session. But you can, of course, ask your questions in the chat box. And so let me just share this again. And we can turn off our cameras now. And if you want, you can keep yourself on. There is no problem. So I am Ankit Sikarwar, a postdoc at INED, Paris, and that is currently freezing. And I have been experimenting with GIS and remote sensing things since last few years and learning a bit every day. So I'm not an expert either in remote sensing or in demography, but I know pretty well how to link these two, and that's my introduction. So let me also introduce to you Leo and Basil, who are also PhD scholars at INED, and they will assist you during the hands-on session within chat box in case you have queries. So now, without taking much time, let's just start this wonderful webinar and have some fun learning new things. So let me. Okay, so we are here today to explore about extraction of spatial data on environment for research. And for next 2 to 3 hours, we will be discussing important questions of what, how, why, and when related to the spatial data on environment. And we will be practicing on QGIS to process and extract one of this data. So let me tell you that you will get this video recording link and the slides soon on the webinar's web page. And in the slides, I have provided links for almost all the resources we will talk about. So for now, you can just focus here and recheck things later if you want. So the webinar is designed into 2 parts, and in the first part we will see the concepts and background of spatial data on environment, need for open access spatial data on environment, and how the applications of environmental data can be useful for demographic research. And we will see sources to access spatial data on environment with some demonstration for each kind of parameter. And we will take a short break to breathe. Yes. And in the second part, we will we will use the data which we have already shared with you few weeks earlier. So we will have this session in QGIS, and we will try to see how to import environmental data, how to geoprocess environmental data, and how to extract the indicators at desired spatial scale. And then we will have question and answer session. So let's begin with a very basic question: what we mean by spatial data. So in its basic meaning, spatial data is any type of data that directly or indirectly references a specific geographical area or location, sometimes called geospatial data or geographic information. And it can also numerically represent a physical object in a geographical coordinate system. But our focus here is spatial data on environment. So these are basically the data on indicators representing environment at a particular location. Some of the famous examples of spatial data on environment can be rainfall, temperature, air pollution, land use, land cover, nighttime light, and so on. So these spatial data are basically obtained from 2 sources, from ground or from Earth observations. So ground monitoring stations and individual instruments can provide ground data, whereas sensors mounted on satellite, UAVs, or aircrafts can provide us remotely sense information of environmental data. So there are 2 types of data in GIS. I assume that you all might have heard about these terms, vector and raster data, and I assume that you might have seen the videos we shared with you before a few weeks. So so the vector data can be of 3 types: point, line, or polygon. As this very simple diagram here presents, point data can be location of ground monitoring stations, hospitals, post offices, or anything that can be located by longitude and latitude values. Whereas a polygon can represent lake, administrative areas, agricultural field, protected forest areas, etc. And line represents river, road, or railway tracks, etc. But what we are more interested here is the raster data. And these days, you might encounter a lot of fancy world maps on social media, Twitter, Facebook, everywhere, presenting different indicators such as temperature, land use, air pollutants, and many other aspects that are either collected as Earth observations or are geographically modeled or interpolated from ground station data. So in its simple meaning, the raster data are continuous surface of pixels representing unique indicators. So as you can see that the zooming in one of the raster data can lead us to the differentiated pixels. And to be more precise, consider this raster as a digital elevation model DAM, which indicates elevation in meter. And as you zoom into a smaller place, you can see the pixels with elevation values. And these pixels follow a pattern. As you can see, darker pixels are illustrating lower values and lighter pixels presenting higher values. Also, it is important to note that different spatial data have different size of pixels, and we call it resolution in the simple words, and more precisely as spatial resolution of data. So spatial resolution is nothing but the minimum pixel size of the raster data, and it can be the grid of 10 by 10 meters or 1 kilometer by 1 kilometer and so on. And different satellites have different resolutions. For example, the widely used Landsat satellite imageries from USGS have resolution of 30 meter, whereas the recent Sentinel satellite imageries by the European Space Agency have resolution up to 10 meters. But the choice of data always depends on research objectives and research area and also availability of data. So now let's discuss about a very important aspect of spatial data, that is the form of spatial data on environment. So as I told you in the beginning, the raster data is generated either from ground station data or from Earth observations. So here is the example of Delhi in India, where there are around 37 ground monitoring stations detecting atmospheric indicators, but I needed a raster data covering whole extent of Delhi. So I generated a raster from this vector data of points by using spatial interpolation for the particulate matter pollution. And the other case you are seeing here a satellite imagery for Ahmedabad city of India and small villages surrounding it. So this is the raw satellite image, and I wanted a raster data for land use pattern. So I did I did geoprocessing here and created a land use map for this area, from which I can estimate area of each land use class for each village. So here the transformation is from raster to raster. It looks fascinating, but yeah, one has to be cautious about the chances of misleading information in both the cases. So in the first case, the number of ground stations must be enough and should cover the whole area. Whereas in the second case, the classification or the geoprocessing must have valid accuracy levels. The other very important point is about the pixel size. So in the first case, the unit of analysis is Delhi, which is very huge. So even if the pixel size is big, it remains valid. Whereas in the second case, the unit of analysis is village, which is much smaller in its spatial coverage. So the pixel size should also be smaller for a valid analysis. And if we talk about this sophisticated processes, so what about the people who don't have expertise in such kind of geospatial analysis? So thanks to various ready-to-use spatial data on environment, which are pre-processed and validated by group of researchers and experts. For instance, the data you are seeing on the screen provides you free raster data on land use, land cover for the whole world at 10-meter resolution. So all you need is some conceptual knowledge about this data and some basic skills to extract this data at desired spatial scales. And that is what we are going to learn today in the hands-on exercise. So this is all about the concept and background of spatial data on environment. Now let's just discuss the need for open access spatial data on environment. So why this data is needed? So we all are aware about the increasing uncertainties of environmental parameters across the world. For instance, 5 months back, we were discussing the unprecedented extreme heat waves across Europe. And few days ago, parts of United States have experienced killer cold storms, whereas droughts and floods are becoming very common in the global south countries. And adding to this, most of the global cities are suffering with critical levels of air pollution, noise pollution, soil pollution. I think all kind of pollutions are at critical levels in most of the urban areas of the world. So these situations need timely and geographically rich data to be monitored and to be assessed. The other point here, which is very important about the need of spatial data, is there are huge disparities in the number of ground monitoring stations across countries. So as visible in this image, Uganda and Kenya have significantly lesser number of ground monitoring stations compared to the countries of Europe. So in such case, we cannot think about impactful planning and policies for environment as well as for human well-being, because the data we are using might have a lot of overestimation, underestimation for the places where ground stations are not present. And here, Earth observation data becomes super important. So next, for instance, if we have indicators only at bigger spatial scales, such as districts and states, this cannot account for differences within state or districts. So we need fine scale data that can provide a better understanding of how each variable impacts individual communities and population groups. So moreover, the Earth observation data is instrumental for research and policy implications by identifying areas with greater environmental challenges and at the same time having higher population at risk. So further, the applications of Earth observation data is huge for the sustainable development goals. And this diagram nicely present the direct and indirect use of spatial data on environment towards the targets and indicators of multiple sustainable development goals. Also, the spatial data becomes instrumental in countries where census and survey data on such indicators are not up to date and not frequent. So the moral of the story is the need of spatial data on environment is huge, considering the current situations of environment and its impact on human. So now let's see how these data are important in demographic research. So first of all, the connections of population development and environment are complex and varying over space and time. So to explore the direction and magnitude of these connections, we need spatial data on environmental indicators. Secondly, this data can provide answers to the questions of where, when, and how. For instance, whether climate change affects migration patterns, socioeconomic conditions, fertility behavior. Is the exposure to air pollution adding to mortality or morbidity? And if yes, to what extent? Does land use change impact sustainability of rural or urban places? Or one might be interested to check proximity connections such as distance to water bodies and prevalence of waterborne diseases. And not to forget about the open access graded population data that has been solving the issue of spatial and temporal scales in the population estimation. So the next big and very important question is about what type of analysis we should perform to link this spatial data on environment with demographic data. And this completely depends on researchers' interest, objectives, and availability of demographic data. So it can be a descriptive analysis at pixel levels, where one can visualize the correlations between environmental and demographic indicators. Or it can be done by different regression analysis, because we might need to check the association under various socioeconomic and demographic conditions, and also with the presence of other environmental parameters. And the level of analysis can be determined on the basis of unit of analysis. For instance, if the geolocations of individuals are known, we can perform individual regression. Similarly, if the demographic information is available at cluster level, as in the case of DHS data, we need to perform cluster level regression. And if the demographic data is only available for administrative areas such as states, districts, or towns, we should use area level or ecological approach. So in the next few slides, I will present examples of research dealing with these different types of approaches and different data. And there are so many, that there is a huge literature these days available on the linkages of environment with demographic data. But I have selected few studies that represent our interest in this workshop and that represent the analytical parts in relevance to our objective here. So let me just show you this. And the first study is about individual level analysis. And as you can see here, the authors tried to link rainfall with outmigration in 2 villages of Mali. And to do so, they used individual level demographic data from the SLAM survey. And to get climate data, that is rainfall in this case, they used CHIRPS database that is integrated, the CHIRPS data integrates ground station data with satellite data and provides estimation of precipitation. And it is important to note that this kind of individual analysis are useful to make statistical inferences and are generally convenient if the study area is small. So the second study is an example of cluster level analysis, and the authors tried to link Kenya's DHS data at cluster levels, which also provides approximate geolocations of the cluster. Sorry. And the authors use the indicator of vegetation as NDVI, a proxy of agricultural productivity, and they employed multi-level analysis to find this association between agricultural productivity, food prices, and birth weights. So the for the example of area level ecological analysis, I choose this recent study by my team at INED. And among the important things that I would like to discuss with you, the first is about data availability. As you all know, the micro data on COVID-19 deaths is not available for public use in most of the countries. So we restricted to ecological analysis at district level, for which we had the data for COVID-19 deaths and infection. So for the independent variable greenness, we used NDVI from India's national satellite data, and we tried to account for many associated factors, including air pollution, temperature, rainfall, socio-demographic and economic conditions at the district level. So as you see the results, the fully adjusted model 3 here presents lowering risk of COVID-19 deaths in the districts where NDVI values or greenness is higher. The last example we are seeing here is focusing on integration of graded population data and point locations of healthcare facilities. The authors did pixel level analysis to measure proximity of health indicators, healthcare facilities for the population above 60 years of age. And they used graded population data from the WorldPop dataset and accessed geolocations of the healthcare facilities by combining OpenStreetMap and data from surveys and reports. So you can see in this snapshot the pixel level visualization of travel time to reach nearest healthcare facility by the older adults. And this amazing work is done for all countries of Africa. That's huge, because the data source they have used are temporary and spatially rich, and also because the analysis doesn't deal with other indicators like socioeconomic and health conditions. It is quite convenient to do the analysis for such a vast spatial extent. And I would highly recommend to you to read these research works if you have if you are interested in integrating environmental and demographic indicators, because these papers are not only discussing the data sources, but also different kind of methodologies that you can adopt. So now let's move to the last and very important session or part of this introductory session, that is sources of environmental data. And there are several sources, but for the demonstration purpose, I have selected only a few with focusing particular indicators of environment. And let me just drink a little water. Thank you so much. So now I'm going to Okay, so now we will see different type of weather and different type of environmental data with few sources which are publicly accessible, and at the same time we will see some demonstration on how to access this data, how to download this data. And as you can see here, the weather and climate data, I have mentioned here about 3 data sources. So the first is chirps data source that we talked in the first study example we saw for 2 villages of Mali. So this is so this data source combines rainfall estimates from rain gauge and satellite observations. So it is a combination of ground data and satellite data, and it has a good temporal coverage. And whatever sources I'm mentioning here, you can always go back and look them in detail. So the other data source for climate and weather data is CRUTS, that is UK Climate Research Unit's time series data set. And you can see that they have a huge coverage from 1901 to 2021. So its temporal resolution is quite appreciable, and you can see its coverage is all land areas excluding Antarctica, and the resolution is quite acceptable. And they provide information on key climate parameters such as temperature, hydrological precipitation, vapor pressure, wet days, and cloud covers, and so on. And to have a look at, we have this data called WorldClim that is widely appreciated by researchers these days due to its easiness to access and download. So what I will do, I will just first share my screen, because we will go to another window from here. So let me just do so stop sharing and start sharing my screen. I hope it's visible to all of you. And if I go here, let's take, okay, if I go here, can Paul, can you please confirm you can see my screen?
Yes, we can.
Okay, so here we come to the WorldClim data platform, and you can see that this is a very easy to use platform to get our climate data. And here you get not the Scooty, excuse me. Here you get the data on as historical climate data, historical monthly weather data, and future climate data. And the exercise that we are going to perform in the next session is on this data source. So if you click here, you will you get this screen, and they have mentioned everything about this data source, like the time coverage, who produces this data, and what is the properties of this data, such as the spatial resolution, which is around 21 kilometers square. And they have classified this data into time intervals and the indicators like minimum temperature, maximum temperature, and precipitation. So for our examples, example in the for the hands-on session, we have downloaded this data, Tmax, which is temperature maximum 2010 to 2011, but I have extracted only 3 images from the whole data set to perform the analysis without having some error of space or time. So when you download this data, just by clicking this, so you will have a zip file containing 120 geotiff images. So for every year you have 12 images, and for 10 years you have 120 images, and that's quite huge in its memory. So I have extracted only 3 for our example. So let me just go back to our slide. So the next indicator we are going to talk about is atmospheric data, and this is really very useful to demographers who are working on health and morbidity, health and mortality patterns across countries or within countries. So atmospheric data, what we mean by atmospheric data, it can be like the component of atmosphere, like the air pollutants. So here I have mentioned 2 data sources. One is atmospheric composition analysis group, and the second one is interpolated air quality data. So let's talk about the first data source. And this is a widely used data source because it covers whole globe, and we have data on important air pollutants such as PM 2.5, PM 10, that is particulate matter, and nitrogen components. So this is very useful here, and we will see the demonstration how to download this data. But let me first tell you about this data. So on one hand, we have this continuous data, and we can also have a continuous data from the generated from the interpolation methods. Just if you look at this data source, and this data source is based on ground observation, and it covers whole Europe. And as I showed you in the previous slides, like the number of ground weather stations in Europe are exceptionally high, and they can provide a good quality data in terms of its accuracy. So, and let me tell you one more thing about this. Like when you use ready to use data sources such as atmospheric composition analysis group, you have averages for year. But in case you are using ground weather stations data, and if your objective is not to look at only at the averages, annual averages, but within year differences like day by day or month by month differences, you can use this kind of data coming from ground stations data. And let's now just go to the atmospheric composition analysis group data set. So all the links are available in the slides, and you will get it later, so don't worry about this. So as you can see that they have a vast category of data here. So just to demonstrate here, I will click on surface PM 2.5, and as you can see, like it redirect me to this page, and they have different versions, and they are updated over the period of time, and they have specific versions for specific regions, like North American region estimate, global estimates for China, for India. So they mention everything here. And to download this data, I can just follow these simple steps here. And as you can see, like annual and monthly mean PM 2.5 data. But before that, you can check the resolution of images. Like you might be interested for if your unit of analysis is a huge place, such as the example I presented about Delhi. So you can use you can use the lower resolution data, and like you can save a lot of time of processing as well as the space in your computer. So it depends on your research objectives. So if I click Here, annual and mean monthly PM 2.5, that is 0.1 0.01 by 0.01 degree resolution. So I'm redirected here, and they have folders for continents, and you can go here and start downloading whether you want monthly data or annual data. So as I told you earlier, if you want to see changes within months, you can always use ground data from the ground stations, but it depends how many ground stations in your area, how many stations you have in your study area. So let me just, so this is about the PM 2.5 data, and let me just go to the another indicator, and which is land use land cover. Suppose for your research you need data on the type of land use in particular area. For example, you need surface characteristics like built up land in square kilometers for different districts, or green cover in different districts. So you can use ready to use land use land cover data sets. And these data sets, as I mentioned earlier, they are pre-processed data sets, and they have multiple sources of data in their modeling. So they have varying spatial resolution, they have varying temporal scales, methods, and categories. And the good part is, when you download this data, they come with metadata that explains the technique of modeling and time periods and a lot of other things. So for an example, we have here ISSRI land cover data that comes at 10-meter resolution. That is huge, and it's available for whole world. And the second example you are seeing here is about, just a minute, GLS survey, and this is specifically designed to get information on green cover. So for an example, you can see here a Central Park, which is a park with lot of trees, and you can identify the information at minimum level. And there are so many other sources from where you can download land use land cover data sets, and I have mentioned the link here to go through. And let's just have a demonstration using ISSRI's live living atlas, which is similar to the first source of data. And if I click here, it leads me to this window of ISSRI's land cover platform. So here you will find all the fancy features this data have. And to access the data, it is very tricky. So be focused here. Let me just tell you, to access the data, you have to scroll down, and when you find this window enabling the entire GIS community, they have this small hint here to go to the application from where we can actually download the data in tiles. So if I click here, let me just repeat this step. When you go to the ISSRI land cover data set, you will be redirected to this window, and there is information on the features of this data set, how they model this data set, and even they can measure the change occurring over the period of time, and you can easily have visualization of this. But what we need data. So to access the data, we have to come here, and here there is a small word saying this application, and you can see it is a link. So if I click here, I will be redirected to a new window that is telling me that I can download this data for 5 years, that is starting from 2017 to 2021, and this data will be updated very frequently. So let me just show you, if I need land cover data, what for Paris, for an example, what I will do, I'll just go to Paris, and if I can zoom this much, let me just show you by full zoom like how it looks like, and it's quite a detailed data. And they also mention about that accuracy, their accuracy levels in the data set. So this is Paris, and I want land cover data set for Paris. So what I will do, I'll just click on this, and by clicking I will be redirected to select the scenes by years. So either I can choose all, or I can choose a specific year. So if I download, this will start downloading. Let me just stop it for a while. Okay, so this is about the land use data, which is coming at 10-meter resolution, and you can assume that how useful this data can be to link with various, not only to the health indicators, but also to the development indicators, which we frequently use in our demographic analysis. So let me see if we have, yeah. So we now this part is about satellite images, for which I think you need some expertise in data, remotely sensed data. But these are the raw satellite images which are not pre-processed. But if you know like how to use this data in GIS, so it may be important for you. So for an example, we have MODIS data, that is moderate resolution imaging spectro radiometer by NASA Terra satellite, and this gives us the information on temperature, and it is quite frequent. Like they have views for 1 and 2 days interval, and they have 36 spectral bands, and this data will definitely improve our understanding of global dynamics and processes occurring on the land and in the lower atmosphere. And the other data which is very useful and have a good resolution, that is Sentinel data, the Copernicus program that is running by European Commission, and they provide us the Sentinel images, and they are updating over the period of times. So we if you want radar images, all weather radar images, you can use Sentinel 1A and 1B products. You can use high resolution optical images from Sentinel 2A and 2B. And if you are interested in ocean and land data for its climate monitoring, so you can use Sentinel-3 data, and also to look at different air pollutants like carbon dioxide and nitrogen dioxide, and optical aerosol optical depths, which is related to PM 2.5 and PM 10. So you can use the recent version of Sentinel-5 datasets, and these datasets are available from different sources. Like if you are interested in Sentinel, you can use Copernicus platform, and if you are interested in NASA's satellite imageries, you can use Earth Explorer, as well as you can have country specific organizations to distribute these images. For an example, if I work on India, I can approach ISRO's portal to have satellite images of my interest. But it depends on the on the policy of organizations, whether they want to make it public or not. So for the public use, we have this 2 or 3 very specific data sets. And let's just let me just demonstrate you how you can use NASA's Earth Explorer to download different type of satellite imageries. And to go there, I'll click on this link and I'm redirected here. And as you can see, we have one map view. So this map view is to select the area of analysis which I am interested in. So for an example, let's see France. So we are interested to get satellite images of France. So if I scroll down here, there are so many parameters to look at. So the first is search criteria, dataset, additional criteria, and results. So for the search criteria, you can go here and, like you can draw a polygon. So I'm clicking on polygon here and I can, select France like this. So this is the area which I am indicating that I am interested to get satellite imageries of this area. But before that, you have to specify the dates of data. For an example, if I put here 2000 January 1, and you have to add the last, okay, let's put today's date only. So, and it is important to be sure about the cloud cover. So let's just put it at minimum levels so that we will get good quality satellite imageries without disturbance of clouds. So if I go here, so I can go from here, and now we are redirected to different kind of satellite imageries, whether they are digital maps, digital elevation models, or any other data sets. So we can choose the type of satellite imageries we are interested in. And for an example, if I see, okay, let me just check this one. If I check this, and so they will start searching because we have selected a huge area. It may take time, but they will lead you to the results of satellite images that are available for France. So here we can see that like we have all the images which are available for France. Since we have not specified the a smaller area, we have a lot of result here, but you can always choose a smaller area because this data generally comes into smaller tiles which have identification in terms of path and rows. So you can, for an example, if I'm interested for Paris, so I can always Google it first, like what is the Landsat path and row values for Paris. So I can get this kind of information there, and I can specify this, and I can use easily the satellite images which are interested in. But of course, this needs some expertise to process this data, because in this case, it is not pre-processed. It is you who will process the data. So this is all about the satellite imageries. And what I am more interested here in the global gridded population data set. So although this is not an environmental indicator, but we can't ignore it here because it's very much relevant these days. Like you might be seeing a lot of 3D data of cities and towns and states on Twitter and Facebook. Like people are making crazy maps of this data, and all this is possible because of the gridded population data sets that are publicly available, and they are available for a huge time range. So it all started from the GPW project, the gridded population of the world, in 1995, where they produced data for 1 kilometer by 1 kilometer with a little modeling. Like they have put weights and weights to particular kind of spatial indicators, like smaller weights to less weights to water bodies and high weights to cities and towns. And then the next data came, like and it is called grump dataset, and it started from 2011, but they used more modeling, and they integrated one more very important indicator, that is nighttime lights, into their models. And today we have this very nice data source, that is world pop, and they provide us estimates of population by age and sex structures, also in 100 by 100 meter resolution. And they have quite complicated and sophisticated modeling in their background, like random forest modeling, and they use a wide variety of spatial indicators to estimate population counts in the pixels. For example, they use machine learning, and they have indicators of roads, land cover, built structures, cities or urban areas, nighttime light, environmental variables, and land use data. So it is quite rich in terms of its methodology also, and in terms of its time coverage, and 100 by 100 meter resolution is not too bad to be used for smaller areas too. So let me just take you to PopGrid, which is a platform that describes and explain about various data sources on population in gridded formats. So this these websites have this very important tool, like PopGrid mapping tool, and here you can like literally check which data you want for your unit of analysis. And if you go here, I think I went too fast. Let me just do it again. Okay, so if I go here on PopGrid, we can see there is a tool called Explore Data, and you can go to PopGrid mapping tool. So WorldPop is the not only one source from where we can get gridded population estimates, but we have other sources, and we can check for an example. We want to see about Paris. Oops. So if I zoom in here, I can compare different data sources, like how they look like for Paris, and we don't see world pop anywhere here. So let's just put world pop here by doing this. Okay, so now we have GHS data, we have Landscan data, we have VII RS data, and world pop. So I can see, like for my analysis, I can use this data or Landscan data, because I can clearly visualize which data have more details for me. So this is just a platform to compare different sources of gridded population data. But let me just take you to WorldPop, which is widely used these days. And if I click here on worldpop.org, I am redirected to this window, and here you can see everything about WorldPop data set. And if you see, they have a lot of things here to explore, but what we are interested in the data. So if you go here and you click on data, let me just put it. Okay, if you go here and if you see, like, they have a lot of indicators related to demography, and if I, so you can explore all of these, but it's not always they are available for all parts of the world, so you have to check it first. For an example, age and sex structures, we have I think for almost all countries of the world we have this data. So I go here and they have two types of data, unconstrained and constrained data sets. So you can see, let me tell you the difference between this data source, constrained and unconstrained. So in 2020, they have one layer of human settlement, very detailed layer, and they integrated it into their estimation. So the constrained data sets, they are only available for 2020, whereas unconstrained, you can have it for 2000 to 2020 with 1 year of interval. So they are available for all the years. So let me tell you how we can download it. If I want it, I want this data for France, for an example. So I'll click on unconstrained individual countries, and I can type directly here the name of the country and will lead to the results related. So for an example, we can see like we have population data for France from 2000 to 2020, and if I click here data and resources, it will lead me to the overview window, like how it looks like, and there is a detail about the data source. And the good part about this data source is it is constructed into age groups. So you even have a age group of infants and child population and elderly population, and overall population by male and female in the 5-year age group. So you can download this data from here by clicking here. You can have, so this data means let me just tell you about the terminology they use here. So this is France, male population 80 years and above for 2020. Okay, so you can take a look at the terms they use for this particular TIFF images. So here they mention about the terminology too. So for an example, if you see here, the AFG F05 2000.TIFF image means people per pixel for female age group 5 to 9 year in Afghanistan for the year 2000. So it's not so complicated, and you can use this data source. So now the question is, like, we have multiple data sources on environment and even on population estimates, but all this data are available in raster forms. Okay, and this can be processed by a uniform method in the GIS that we are going to see in the next part. And I think it's right time to take a break. I hope you liked the presentation, and we have a lot of to discover now. As we saw a message from Paul, like we may face a lot of errors while processing data in GIS, and that is very common. Don't panic. You can see this. You can watch this video as many as time you want. So you will have it, and I think we all are here now. And I hope like all of you have downloaded the data the way we told you in the email, and you have it on your desktop, so that we won't waste much time on finding data. And forgive me if my QGIS hangs in between, so it's common, but I hope it will work nicely. Should we start, Paul?
Sure.
Okay. Okay, so let me just share my screen, because in QGIS you have different windows. I'll just minimize myself. Okay. So when you open your QGIS, I don't know how many of you have good, intermediate, or no level of QGIS, because it's hard to assess, but I'll try to be as basic as I can be, so that you won't miss anything. But for those who are expert in QGIS, it might be a little bit boring, but bear with me. So when you open your QGIS, it looks like this, and you may have your previous projects appearing here, but what you can do, you can click on the new project button here, and or you can press Control N for new project, and this will be a new window. But as you can see, like the general layout of QGIS is made up like this, just like any conventional softwares we are using. So what I need here, I need one more panel of browser, which is not available here. So to turn on or turn off the panels, you can go to View command. I'll just reduce my speed of talking now, so that you can be with me. So I can go to View, and in the View we have this panel option, and you can just check on browser, so that you will have browser from where you can browse your files, browse your data. So now we have one window for browser, one window for layers, and whatever layer we add, layers means the data we add here, they will appear here, and you can change the layer properties and check the layers from here. So let me just first bring the data here, what we have for climate. So to do so, I can use this browser window, and I can locate my folder. But what I will do, which is a bit time taking and more conventional too, but it's good to look here. So you have this option of layer here, and you have this option to add layer, and here you can see what type of data you want to add here. So for the first step, I will add my raster data here that I have already in my folder as GeoTIFF images, which I shared with you. So to add the raster data, I will go here and click on add raster layer. So this will lead me to data source manager window, and by clicking on this browse button, I can go to my folder. Okay, so if you don't, it is already open, but let me just go to my desktop where I put my data IUSSP folder, which all of you have already. So I will open this. I will go to raster data, And I have 3 images here. Okay, so I hope you all have unzipped the data which I shared with you, and if you unzip, it look like this. So I will select all 3 of them and I will open. So without changing any default property, I will just hit the add button here to get my data on QGIS. So what you are seeing a raster surface of temperature data. So I told you this data comes from World Clim platform that produces data on maximum temperature, minimum temperature, and precipitation. For our analysis, we have used the maximum temperature data set from the slot of 2010 to 2018. And for that, I had 120 images, but I have extracted only 3 images and deleted everything else just to simplify the process. But you can have as many as you want and as many as your computer can support. So let me just tell you a few things about QGIS first, for those who are using it for the first time. And like, this is a raster surface we are seeing, and we have 3 layers, 3 data sets open here. And by clicking on this small arrow, you can actually see the legends of this data source. So this is basically for this layer, if I say it is the 2018 May month, 5th month of the year, and the darker the color, it is the lesser the temperature, and vice versa. So you can see that this data have a huge variety, huge difference. Okay, and to zoom out any place, you can use this zoom in button from the taskbar here. And for an example, I want to zoom on France. I'll do like this, and I'll keep zooming, and I can see the pixels here. Okay, so this is the zoom in feature if you have a big spatial extent. And similarly, you can zoom out too, or you can always click on this button, which is a zoom to extent or full zoom, to have your data in a full view. Okay, so you can use these 3 buttons very frequently to go here and there over your data. And if I want to move my data, I can always use this hand sign and pen map. So also I can scroll by my mouse to zoom in or zoom out the data. So it's not so complicated here, but I'm just telling you for those who are doing it for the first time. So let me just zoom on France for a while. Okay, and I see here some differences in pixels. So it is the difference in maximum temperature. Okay, so what we are seeing is a raster data, and to check the properties of this data, like what we mean by these pixels, what these pixels are containing. So we have this very important tool here that is called identify features. So if you click on this tool, and if you click on any pixel, for an example, I will click on, let me just first zoom in a bit more. And if I click here on this identify feature button, so the brighter picture, the brighter pixel is showing the temperature of around 18 degrees Celsius, whereas if I click on the darker pixel, it is showing the temperature around minus 1.16. So you can identify the values of pixels by using this simple command, just to have look what your data, what is hidden behind this raster surface. So that's the basic information about this thing. And let me just go to full zoom. And now let me tell you what we want to do first. So okay, I forgot one step to show you first. What is our objective? So let me go to this window and okay. Let's just visualize for a while that what we are going to do here. I hope it is visible to everyone. Okay, so our objective is to process climate data for the administrative units or cantons, which are more than 3,500 units in France. So what we will do, we will import remotely sensed data, we will read the data, we will edit the data and do some geoprocessing and extract these indicators at desired levels, spatial scale, sorry. So we have this raw satellite, raw raster data of maximum temperature, what we just did in the QGIS. Then we will extract this data with different geoprocessing, and then we will aggregate this data for the cantons of France. Okay, and ultimately we will have this data into Excel format, from where we can integrate this with any demographic or health data. Okay, so let me just go back to our QGIS window. Just okay. So now we have the raster data of temperature, maximum temperature for the months of March, April, and May. So what we want to do, we want to this data for these 3 months. Okay, for an example, you are intended to get annual average of this kind of data, so you will have 12 images for 2018 and you can average it. But for the sake of simplicity, we are doing this on only 3 months. So we have March, April, and May data for maximum temperature. And now I don't want the data for whole globe, which is too big for me. And as our objective is to do the analysis on France, what I will do next, I will add a vector data, that is the shape file of France over this raster layer. So to download the shapefile data, though I have already provided you the shapefile in the zip folder, you already have it, but just to demonstrate where you can download. So this is one of the platform, Diva GIS, where you can download the shape files of any country. For an example, I am interested for France. So I'll go to Diva GIS and I'll choose France. Okay, and I specify here as I need it for administrative areas. And if I click, if I download this data, it comes into a zip folder, and let me just show you from the folder only. So we all have this data into our data folder. And here you can see that we have administrative boundaries for different units. So it starts from 0 and it goes increasing as the spatial unit gets smaller and smaller. So for an example, the admin 0 level is the outer boundary of the country. And then you have respective subnational units. So for our analysis, we are going to use admin 4 level, which represents the canton level. So we are going to use this one. And let me just tell you for the non-experts here, those who have not used save file. So whenever you download save file, it comes into several formats, and what you need most is the SHP format, not any other. But whenever you download it together, because they are inter-supported with each other. So if you have only this file, it won't work and it may result into error, or you may feel confused. So now I'll go to my QGIS, and as I told you, I want to add France border here. Okay, so what we did for adding a layer in raster form, we will repeat it. So I go to layers, I go to add layers. You can always use the shortcuts available in the taskbar, but I'm showing it in a conventional way. So in this time, what I'm going to do, I am going to add vector layer instead of raster layer, because I'm going to import a save file. So I click on add vector layer, and similarly I go to browse and I go to my data folder, and I will add here the save file for France. But first we want to see the full extent of France. So what I'm going to do, I'm going to add the outer boundary of France for a while, and I will click on .shp format, which means shape file. Okay, so I will click on this and I will open it. Okay, so without changing anything, keeping it in its default form, I will just add the shape file. Okay, it is added 2 times because I clicked 2 times. So let me just remove. Okay, let me just show you to, like, if you want to remove anything from here, you can just right click on the particular layer you want to delete, and you can remove it from here. Okay, so now we have 2 data sets, but it's not visible because our save file is hidden behind the raster surface. So you can always reorder your layers like this from here just by dragging them. So I have border of France here on the surface. So but don't you think that this shape is the shape of France is a bit compressed or distorted? So what I want to tell you here is about map projections, which are extremely important while doing any analysis in GIS. So let me just zoom here. So I don't see it as the actual shape of France. So what I need to do, I need to change the projection. Before that, let's just see why projections are important in this kind of analysis. So let me just go back to my slides, and I have prepared this kind of things, side by side things, just to keep you informed about the small things which are very important. So we all know that Earth's surface is 2-dimensional in its form, and when we try to flatten it, it always going to have distortions in its shape and area. So we have different map projections to minimize the errors in shapefile and areas. So basically, we have three types of projections by their families. So we have cylindrical projections, which are generally good for the areas of equator because they touch the globe from the equator, or it can be it can be good for any area which the surface is touching it. And we have conical projections, which are generally good for the tropical areas. And then we have planar projections, which are specific for any country where the projection is touching the round surface of globe. I think it's very basic, but let me just tell you this thing. So we have a beautiful human head here, and how it looks like when we use different projections method on this human head. And surprisingly, this is the fourth figure here, man's head plotted on Mercator projection. This is the projection we generally use for world level maps. So the map we always see are not always in the true shapes. So we need to have predefined projections for each area of the world. So to get it into true shape and true area, what I need to do, I need to change the projection. So what I can do, I can just change the projection of this layer, whole layer, by clicking here on your right side corner. If you see that EPSG 4326, so if I click here, you can change it from multiple windows, but you can easily go here on the projection window by clicking this thing here. And as I can see, there are different kind of projections here, but what I am more interested is in France. So I already know that for France, the ideal one could be WGS 84 UTM 32 North, and I can have a preview here. So you can see that this line is covering a part of Europe, so I think it will work for France. And if I just click here and do apply, okay, so now you see the correct shape of France here. Okay, so let me just repeat what I said. To change the projection, I'll go here, and because I have previously used it, I am seeing it here, but you can always type the type of projection here you want to search for. And let me tell you how to decide which zone number you can use for your country to have a perfect projection. So to do so, like, we have this scheme of UTM world zones, and like they have this north and south from the equator, and they have some numbers. So as we choose our projection as 32, so I got the idea from here. Like, for the European part, I can use any zone between 30 to 35, and that will present a true shape of the area. So for an example, if you are working for Sri Lanka, okay, the island of Sri Lanka, so what you will choose? You will choose, first you will see the zone. Okay, it's coming in somewhere around 44 or 43 here, and north. Okay, so you can search in the projection bar, projection search bar, as a UTM zone 43 north. So it will be ideal for Sri Lanka, and it is true for, it can be, you can choose the right number for your area of analysis. Okay, so let me just go here again, and now we have a good projection system to project our data in its correct form. So let me just change the symbology a bit to see what is behind this shapefile. So I double click on the shapefile layer, and I go to the symbology property here, and what I can do, I can just make it hollow by clicking outline blue, or like there are multiple options to decorate your data, but we are not going to cover this here because we have already shared with you the basics of QGIS mapping. So it is not part of our webinar today, but what I am suggesting, to have the outline, we can choose this option, and if I click OK, I can see that okay, my area of France is visible to me. And now what I want to do, I want to extract this raster because I don't want the global extent here. My area of analysis is very specific to France. So what I will do, I will just extract this raster one by one, because we have 3 layers here. And so to do so, what we need to do, we can go to raster, because we want to clip our raster. So I go to raster and I go to extraction, and I can use this option, clip raster by mask layer. So our mask layer here is the administrative boundary of France. So we can use this. And let me just tell you, in QGIS, you can search for any tool here. So if I write extract, okay, so there are the options will appear here. Okay, so you can always use this window if you don't remember where the tools are. Okay, so let me just go to raster and extraction, and I will just do clip raster by mask. And here in the clip raster window, we will have input layer. So which layer I want to clip. So this is the first image of March month. And then we have automatically the save file here, because we have only one save file added to our layer. So it automatically appears here. If in case you have more, you have to select from here. Okay. So we don't change anything here. We can just add the no data values to 0 as 0. And without changing anything here, let's just run this algorithm, and it's done. So I'll just close this, and if I uncheck all this, I can see for the month of March, I have extracted my data by boundaries of France. And let me just rename it first, because we will forget like which month this is. So I will just right click on this layer, and I will go to rename layer, and I'll just put 03 here. Okay, sorry, yeah, 03 here, just to remember. And now I will repeat the steps for rest of the 2 images for the month of April and May. So I'll go to raster, I'll go to extraction, I can clip, I hit clip raster. So now I will choose the 4th month, and mask layer is France admin shapefile, and I will put here 0. I will just hit run. So the layer is added here, and please do not forget to rename them before you have multiple layers with the same name. So for the sake of simplicity, we will change the name, and let me just put it like 04, and we will repeat the step for. You can have plugins to automate this process. There are so many plugins available for QGIS, but since we have only 3, we can use this one, this option. So this time I will select May month and same save file, put here 0. Okay, and I will hit run, and I will close this window. So let's just rename this first. Oh, we want to rename this, not to remove this. So I will put 05 here. Okay, so now we have 3 clip data, and we don't need this data anymore, and it's always advisable to remove the additional files that you don't want, because it may they can slow down your computer, and to avoid that, I'm removing this layer. Okay, so now we have 3 layers. Okay, and you can see that we have a pixel level difference for temperature. Okay, so what is the next task that we want to perform here? We want the average of this raster. Okay, these 3 rasters. So what we will do a geo calculation that is performed by raster calculator here, and this step is very important for any kind of raster data that you are going to use, whether it is temperature data, whether it is rainfall data, whether it is gridded population data, whether it is air pollution data. So I'm just presenting this by the example of temperature, but you can use these methods in your own analysis, even if your indicators are different. So let me just average this. So what we are doing pixel by pixel averaging. Okay, so to do so, I will go to raster. Okay, since we are processing on raster. So if I see here, the first option is about raster calculator. You can of course search it from here, but what I will do, I will just click raster calculator within the raster window. So here you have a very simple calculator kind of thing. So, and you have the raster bands added in your layers appearing here. So what you need to do to average, like we will just add these 3 images and divide them by 3 to get the average. So to perform this, what I will do, I will just put, I will just double click on this. Okay, I will just put addition, double click on the second layer. So it is added. I will add the addition and then the 5th layer, and just to, because we want to divide it, I will just put a bracket before and after. And what I can do, I can use see, unless your expression, the formula for your calculation is right, it will show you expression is invalid, and as soon as I put a valid formula, it becomes valid. So you can use this formula. So what you are doing, you are performing calculations on raster surfaces. Okay, so this is the formula for averaging the 3 images that we have. But and now we will select the folder where we want to save where we want to save this file. So I'll just select my folder only, which I am. Okay, so there is IUSSP data, and for the sake of simplicity, I will make test folder where I will save all the result of our analysis. So I click here, and if I add, this is average T max. Okay, I'm just giving a name of average T max, and I'm saving it. Okay, so you have to create a folder and you have to give the name to the layer. Okay, so this is done. I don't change anything here for a while, and I'll just hit run, and the raster calculator is doing its job. Just a minute. So now we have in our layer window the average T max. Okay, so you can see if I will uncheck. Okay, so this is the average temperature for these 3 months, and we can see the pixels are more pronounced here. So let me just do zoom to layer, okay, to get the full extent. And now, as I told you, now we don't want the layers which are available for specific months, because we have the final layer as average. So I will just remove these layers. Okay, so we have this, and let's just try to do some beautifications here with the use of symbology tool. So what I will do, I want to visualize it nicely. So what I can do, I can just right click here or go to property, or simply by doing double click, I can go here and I can choose the symbology tab from here. And to do so, like we have to first change the render type, and I can change the render type from single band gray to single band pseudo color. And within single band pseudo color, I can choose the color schemes available in the QGIS. Okay, but before that, let's just categorize this data to visualize it nicely. So what I will do, I will just click on equal intervals, and I can specify here whether I want 5, 10, or 15, or whatever amount of classes I want. So for now, I will just put 10 to visualize it nicely and to detect the changes. So let's just try to change this color, because this is temperature, and I would like to tell you this very interesting thing. Like if you, okay, I will answer to this later. So okay, let me just see. Okay, we are doing this for a specific purpose that I'm going to tell you in 2 minutes, just after doing the this specific task. Okay, so why we are doing all these things, raster calculation pixel by pixel, it has some meaning for not for this data, but for the other data that you can use, what we have discussed already in the previous part. So you can go here and you can select this new color ramp just to get few nice color schemes, very specific, which the experts generally use. And you can go to, you can have different type of color schemes designed for different kind of spatial data. So for an example, we are working with temperature, so we can choose this scheme for a while, and if I hit apply, I will have a scheme like this. But what I can do, like I want, yes, this is nice. This is perfect for now. So we have visualized our raster surface, and let me just tell you why raster calculation is very important, why we want pixel by pixel calculations. So here in the slide by slide things, side by side things, I have added this thing to tell you what you can do more with the raster calculations. For instance, you want to convert temperatures from degrees to Fahrenheit to Celsius. So you know the formula about it, and you can select your raster, you can subtract 32 and do the standard formula, and you can change the unit of your indicators. Or there are indices like we heard a lot about NDVI in the previous session. So if you want to calculate NDVI, so for that you will be using multispectral satellite images like Sentinel or Landsat images that comes into several bands, and from that from the set of bands you can extract only the near infrared and red bands to calculate NDVI. Likewise, you can do it for any other indices like EVI, enhanced vegetation index, or built up land index. There are so many index designed for particular indicators. So you perform this analysis within raster calculations. Okay, so to get NDVI, you just run this very simple formula, and you can have values from -1 to +1 that indicates NDVI. And what you can do more, like you can apply weights to the pixels and make criteria based selection for indicators. For an example, if you are using the raster of land surface temperature from any satellite data source, so if you want to highlight the pixels which have the values over 40 degrees Celsius, so you can just apply this criteria and you can select those pixels. And also, in case if you are working on gridded population data, you can like club population groups or subtract population groups into specific groups, or you can identify population over age 60 or these kind of things. So raster calculation is very important for our analysis, not only for this, but like you can think of several possibilities here. So now let me just zoom to layer here, and we have this nice map here representing temperature from -5 to 20 degrees Celsius, and like this is the calculation up to pixels. But what is our ultimate aim? Our ultimate aim is to aggregate this temperature values for Canton levels. So now next what I need a vector layer of Cantons here. Okay, let me just proceed with this to maintain the time, and I think Basil and Leo will solve your individual queries. Don't worry, these are very small queries. You just need to hit a button to get back to your map. So let me just tell you what I need to do next. Okay, my map disappears, so I will just do zoom to layer, and I will add the vector layer of the Canton level shapefile. So I'll go to layers, I will go to add layers, I will add vector layer, and from here I will choose the SHP of admin level 4, which represents Canton level boundaries. And if I open without changing anything, I will just keep it as default and I will hit add. So what you can see here the boundary of Canton, and let me just zoom here. Okay, so this is Paris, and let's just make it hollow for a while to see what is behind. So to do so, I'll go to outline blue, and here I can change the some symbology to visualize it effectively. So what I will do, I'll just hit white and minimize the width of lines. Okay, to apply. Okay. Oh, just okay, so I'll hit this. Choose colors, and I forward to make it hollow. Just a minute. Okay, so it's there, and if I zoom to there, I can see behind the boundaries, but it's not so good because there are so many unit in this zip file. So when we zoom in, we can see the pixels behind each Canton. And let me just zoom to layer for a while. And now we come to the very important part, that is to aggregate this data into Canton boundaries. So for this, the very famous tool which is called zonal statistics. So you can search here on this search bar zonal statistics, and if I go here, okay, so I am on the zonal statistic window, and here you want to identify what is the label of your shapefile, like which shapefile you want to select that is representing your unit of analysis. For ours, it is admin 4 shapefile, so I will select admin 4, and I have to specify the raster layer for which I want the aggregation. So I will use this, and since we have only one band in this raster layer, so it is appearing only it is automatically selected. But in case if you have several if you are using multispectral images, you can have a lot of bands here, and you can select whichever you want to process. So you can put a prefix here, or you can avoid this. That is and this is very important here, statistics to calculate. So if you click on this button, so you have the parameters of statistics which you want to derive for your data. So I'll just click on these things like count, sum, mean, median, standard deviation, minimum, maximum, and range, and I will click OK. You can also simplify it by only selecting the mean, because our aim is to find the average within the area. And if I do run, okay, so I have something in my layers, something new. Okay, from where, okay, can not find the raster extraction plugin. Yes, right. Okay, let me just, okay, Leo is answering to this. Okay, to search for anything, like you can go, like for zonal statistics, you go here, zonal statistics, you write. And always, you know, like it is important to select from the processing algorithms, not from the project layers, okay? Because this shows the result of our analysis available in the layers. But what we are interested in, we are interested in processing algorithms. So we will go here and I will just double click to go to zonal statistics, okay? I hope it's fine. So now we have this thing as zonal statistics, and to see what it is, like we can either do it by the identify feature tool here, okay? So if you can see, like now we have data for this canton, okay? So what we selected for the in the zonal statistic thing tool, like sum, mean, median, standard deviation. So these are the temperature figures according to different parameters. So our mean temperature for this canton and its name is okay, I will not pronounce it because it is in French and I'm still learning French. So it is one canton, and we have mean temperature for this as 15, okay? And what we can do, just to check our data, we can right click here and we can open attribute table. And now you can see, okay, it's becoming difficult for me to move. So let me just go here, and now you have cantons and the data of sum, mean, median, standard deviation, minimum and maximum, all the parameters that you selected during the zonal statistic tool, they are here for cantons, okay? So now we have our data in table format, but it is not in Excel. So our demographic data generally comes into Excel or Excel format or state, it is in Stata, or you can always have it in Excel format. So let's just try to export this data into Excel format. To do so, you just need to follow a very simple step. You right click here on the zonal statistics and you hit the export button, okay, the tool, and I will select save feature as option. And here I see a lot of format options, okay? So for us, it is MS Office XLSX format. So this will be the spreadsheet format, and I can give the name Tmax for a while, and I'll keep everything like this, okay? I'm not changing anything here. So by doing so, now did I select the folder too? Let me just check. Okay. Okay, let me just do it again because I think I forgot to. So to export my zonal statistic table from this format to Excel format, I will go to export by right clicking on the zonal statistic layer, and I will save feature as, and yes, I can specify here the folder, okay? So I will put this into the folder of our data and test, okay? So I will give this raster name as Tmax, and I will hit save. Okay, so now we have a location of our spreadsheet, and here we have the spreadsheet automatically open because we choose so now let me just do zoom in to layer. Okay, so we have our data as Excel, as a shapefile, and as a continuous surface. So what we are going to do next, okay, so let's just present the data as per the Canton boundaries. Okay, so what we will do, this is also important for you. This is just a mapping tool that we use generally for representing any kind of data for administrative level shapefile. So what I'm going to do, I will join the shapefile to this data to present the indicators. Okay, so to do so, I'll go to shapefile first. Okay, FRA admin 4, and what I will do, I can go to property by right clicking, or I can just double click on this. And so what, let me just do it again. Okay, I am going to save file FRA admin 4, and I'm double clicking on this, and I'll go to join, because I want to join my Excel table to my save file. So I go here. Okay, and I will, let me just minimize this. Okay, so what I will do, I will click this add new join tool here. So it will ask me which layer you want to join. So it is the Excel format that I want to join with my save file. So I will select Tmax. Okay, it has some symbology like table, and this is very important to know. Like, to join fields, you should always have at least one identical variable in your save file as well as in your Excel sheet. Okay, so in this case, let's just check what is the identical variable that is present in both this shapefile. So I know it, but I'm just showing it to you so that you can have idea about this. So since I am working on Canton level, what I can do, I can use the name 4 or ID 4 variable. Okay, because I have this in my shapefile as well as in my Excel data, and these are different for all the cantons. Okay, so I will choose either ID 4 or name 4, but it's always good to choose numbers over text, because sometimes they may be different. Here it is not possible because we extracted the data from save file itself, so they must be similar. So let me just repeat this step. I will double click, I will go to join on the shapefile, and I will add here, and in the join layer I will select my Excel file, and here I will select ID 4 and ID 4 in the target field. So we have specified that we want to join our data with this variable. Okay, I will hit OK, and I will do apply. Okay, so now if I open my save file, attribute table, so I will see here the variables which we extracted, and they are now joined with each canton. So we have our data of interest here, and we can present it with various schemes. So let me just try to present this one. So now what I will do, I will change the symbology of this save file. To do so, I will go to the symbology bar, and from here I can change it to graduated, And here you can select the variable of your interest, which you want to show here. So in our case, we will use Tmax mean, that is the average for the geographical area we are working for. And you can, as we did earlier, you can choose quintiles or equal interval or different kind of schemes for classification, and it's always to have more number of classes to see the differences. So what I'm seeing here, it is a, so before that I need to change this scheme. These are basic mapping tools, so you can learn it later also. So it's not a big deal. Our objective is fulfilled till now, but what we are doing is just to present our data. But we still have one very important thing to do that we will perform next. So be here and don't sleep. So let me just change it to a full, field one. So simple blue field. Okay. So now we have a difference, and I can always change the schemes from this. Okay, so I have changed it, but it is not visible because the layer is behind zonal statistics. So here you can see that you have the data for each cantons. Okay, and you can just see the variations. We have a huge variations here, and always you can check the properties by doing this, by using the identify feature tool. Okay, so you can see the mean temperature for this part is okay, it's 14, whereas for this part it is, it is 12. Okay, so we can see the differences very nicely here, and this is just a scheme to present your data, not any kind of geoprocessing or raster processing, but it was important to always to have a good map as an output. So let me just do zoom to output, and now we have two maps, as you can see. Like, let me just unpick. So one is our continuous surface and one is aggregated data. Okay, so we achieved 80% of our goal till now. Okay, there is, okay, good. So everyone is engaged with me too, and I'm happy. So let me just tell you how to export this data. Okay, that is, and then we will I think we have time, so we can see how to extract data at individual levels. That is very important these days, and I think a lot of people don't know how to do this, even if it is very simple to do. So I will try to cover this part too. Okay, thank you. So let's just quickly give a layout to these two maps, and I think you can follow these steps later too. These are nothing, just the symbology part. So to get a map in the form of image or PDF, what I will do, I will go to project, I'll create a new print layout, and I can give a name as taste or something, whatever you like. Okay, so by doing so, I am here on the page layout window. Okay, so the first thing what you can do, if you click here, you can specify the size of your image, whatever you are interested in. Sometimes journals provide specific size of images, and it is always better to specify the size before, because when you cut the images, the JPG image or PNG images, they sometimes get blurred or lose their resolution. So it's always better to specify the sizes before. But for this case, I'm only going to use A4 size map. And always remember, whatever you left on your QGIS window open, it will appear on your map layout. Okay, so let's our objective is to have an image where we can have on one side this continuous surface of temperature data, and on one side the aggregated. So let's just have this map open and unchecked everything. We can add the borders too, so it's better to have it above the layer. So now if I go to the map layout window, and if I click on add map, I will be able to import that map into this page. So what I'm going to do, I'm just putting half of the portion of the page for this map, and you can change the size of your scale of your image by reducing its scale. So let's just make it 10. Okay, so let's just make it 8. Oops. I put one more 0. The value of 0 is very important. Okay, so here we have one map. Okay, so what you are saying, like if you are moving, the whole grid is moving. If you are moving your cursor, the whole grid is moving. But you can avoid this by clicking here, move item content, this small bar here. Okay, so by doing this, you can just move your map within the grid boundary. And yeah, and when you are done, you can, I think I need to expand it a bit. Okay, so I have positioned my map, and I will again click here on the move item or select item, and I can just this here. Okay, so I have one map here, and what I need to do next, I can, like there are hundreds of ways to symbolize this map, but let's just do the basic ones, and you can explore it more later. So I'm going to add the legend for this map. So to do so, you can do it from here or from add items here. So I just click here, add legends, and I go here, and I see a lot of things here, even those which I'm not interested in. But you can always select this thing, and you can click this one, like only show items inside the linked map. So we have this here. Okay, so I will just put it here. Okay, let's just put it here for a while. And there are so many things which we don't need for this, and I can remove this by playing with these tools. Like I will uncheck auto update, and I can remove things from here which I don't want. Okay, so the legend is quite not convenient for me here, and what I will do, I can go to symbol and increase the width and height of symbols. There are so many options that you can explore. It's limitless. You can be as artistic as you can. So I put it here, average temperature, and our next part is to import the other map from QGIS, and like it's always better to lock your map before you add another map, because whatever is open in your QGIS will appear here. So what I did, I just clicked on this map, and by going to item property, I just locked this layer, and I will do similarly for this legend. Okay, so I will also lock its position from here, and now I will add another map, which is the classified map. So to do so, let's just first open this map in QGIS, and we go to our map layout, and I will click add map. Okay, I hope it works. Okay, so we have our new map here. Okay, let me just put the same scale we used for the map. Now we have our classified map here, and as I told you, if you want to move your map within your within the grid, you can always click on this move item arrow, and you can have your map rightly placed. I think it's fine for now, and okay, so that's fine. So now we need to add legend for this too, and by clicking on add legend button, we can add legends here, and we can choose only the one which are presented in your map. So by just clicking this, you can reduce this to, and since it is too, there is no place, what we can do, we can just click here on the legend, and we can go to columns, and you can make it in 2 columns and split layers, and you can always do this kind of things in QGIS. Okay, so now we have data in 2 formats. One is in continuous format, and one is in aggregated form. So let's just add the most important parts of any map, that is scale, and of course north arrow somewhere here. You can change these things, but we are not interested so much in symbology part. And just give it a title as to add text. You can use this add label command and type your title here. For us, it is temperature maximum 2018. Okay, for March. May. Okay, and I can always choose a right size of font, style of font. I'm not giving much efforts to this for now. Okay, so I think it's good to have this map for a while, and we can export this map. Okay, so to export this map, you go to layout, and you can export this as image, as SVG, as PDF. So I will just export it as image in my folder of my test. Okay, I give it a name figure 1. Okay, I can choose the resolution and everything, so just make it smaller. And I can hit save. Excuse me. Okay, so now we have, let's just check how our data looks like in a JPG format. So here is our map. Okay, pretty well. It's look beautiful. So, and we have our data in Excel format with the indicators we choose. Okay, so this can be anything, like anything from the raster data. You just need to think about it conceptually. Okay, so it's not so complicated for non-experts too. So this is one part, and let's just come to okay, could you please repeat for the second map? Okay, let me just try for a while. You know, like when you want to add another map, you first click on the first map, okay, and then you I'm not doing it here, just telling you, when you click on the first map, okay, so there will be an option to lock your layers, so you can lock it, okay, and then you again click on the add map, but before that you need to change your map in QGIS. Okay, so whatever is visible on your QGIS window will appear here, okay, only when you lock your layer first for the first map. Okay, so let me just come to the very important point, that is individual level data, and which is very much of interest to demographers. Okay, let me just close all this window which we don't want. Okay, for now, let's just assume that we have one one raster data, and we want to calculate the average environmental indicator surrounding individual locations. So if you might be knowing that DHS data or any other data that has geolocations, they provide you the data, and we can always play with that data to extract our environmental parameters at neighborhood levels. So let me just do it, because we let's just assume that you have a set of DHS data, and generally the DHS data will come into the point formats. So what I'm going to do, I'm just going to create random points around this this border, and we will assume that they are the individual locations. And what we will do, we will just calculate the environmental indicators at the neighborhood levels of each individual, or you can consider them as a cluster locations. So to do so very quickly, what I will do, I have this one shape file. Okay, so I'm just creating a layer of points for now. Okay, so I'll go to vector, because point is vector data, as I told you in the beginning. So what I will do, I will just go to this vector and research tool, and I can click on this important tool, that is random points in the layer bounds. So I click here, and I have this option to select the boundary. Okay, so I am selecting the outer boundary of France, and I create 100 number of points. Okay, and without doing anything, let's just do this. But here is the very important thing. So I wanted to tell you this also. Let me just, okay, no. So here, whenever you deal with distance in your raster data, okay, you have to have an projection with the unit in kilometers, meters, or miles, not in the degrees, okay, as here, because our projection of this shape file is not in the unit of kilometers or meters, so it is showing us error, because we want to specify the distance. And to do so, what we will do, this is very important for other things also, so just be focused here. So what I will do, I want to change the layer of layer property of, sorry, projections of this shape file from one projection to another, which has the unit in kilometers, meters, or miles. So just to check what projection and what unit you already have in this file, so you can always double click here, and if you go to information, you will have a coordinate reference system. So here we have WGS 84, and the unit are in geographic, but we don't want this. We want here as meters. So what you need to do, you can go to, because you are working on vector, you go to vector, and you go to data management tool, and you can hit reproject layer. Okay, so I just hit reproject layer, and I specify the shape file here, and from here I can change the projection. So we have layers which we recently used. So the UTM projection, that is universe transverse Mercator projection, and it has a unit in meters, so it is good to use this one. So I will just use this one, and I will just run it. Okay, so I'll close this one, and now we have a reprojected shape file of outer boundary of France. So I can just remove this one. Okay, so now this is our reprojected file, and we can just check the information. And now we have units in meter, because we changed our projection system to UTM. Okay, and now we have meters. Okay, and now we will not face the error we saw earlier. So now I'll go to vector. Let me just do it, make it hollow so that we can see behind. Apply. Okay, my QGI is getting slower. Okay, so I will create 100 points within this boundary, and we will assume it as individual or cluster locations. Okay, so I'll go to vector, I'll go to research tools, and I can select this tool, random points in layer boundaries. So now if you see, like earlier we were seeing, and we were facing one error here, so we change it, and now we don't see the, and we are going to select the reprojected, the new layer. Okay, and just specify the numbers, 100. Okay, and you can specify the minimum distance between points. Okay, but let's just do it randomly, and if I hit yes, it's processing. Oops, I should have given 50. Don't worry about the symbology aspects. You have a lot of material available for designing your maps and giving them different, layouts. And it's there. Okay, so I will just close it. And now I have points here across France, and let's assume these are the locations of individuals for which you have health data, or location of clusters or anything, any entity. Okay, location of hospitals. And if you want to check the number of people surrounding hospitals, so you can consider it as location of any spatial entity. Okay, so for now just assume that these are the individual locations for which we have health data. And to let's just assume that we want to aggregate average temperature surrounding each individual in the zone of 10 kilometers or 20 kilometers. For the sake of simplicity, let's just make it 20 kilometers. So what you need to do, you can go to vector, okay, to create the buffers, and you go to, okay, let me just, geoprocessing tool. You go to vector, you go to geoprocessing tools, and within geoprocessing tools you have this option of buffer. Okay, so now it has automatically selected the point data because we have only one point data in our layers, so it is okay. And it is showing, let's just make it kilometers for the sake of simplicity, and I make it 20. So if I want to see the aggregate the environmental indicators within the 20 kilometer circle surrounding the individual location, and this is segment which smooths the circle, so you can change it to, so I'll just put run, and it's done. Okay, but you can just drag it behind your point data and you can see it. Okay, so if I drag it like this, okay, so now we have individual location and a save file of circles of 20 kilometers surrounding each individuals. Okay, there are different mechanisms to dissolve this within the buffer zone that you can explore later. I'm not going to tell in detail now. So what we want to do, we want to aggregate temperature data for these zones. So it is not any different. We just need to do a zonal statistic again. Okay, statistics, and if I select zonal statistics from the processing algorithm, okay, remember that from the processing algorithms, so I go to zonal statistics. Here I will select my buffer layer as the input layer because I want indicators for my buffers, and the raster layer should be the average temperature maximum, and you can repeat those steps we did, but for now let's just calculate the mean temperature. Okay, I'll just put okay here. So you can choose, like for an example, it depends on the variable which parameter you should select. So you can either choose minimum, maximum, or sometimes, but for now just select mean, and I will hit run, close. Okay, so now we have this one more layer as a zonal statistics. It looks same as buffer, but now this is a data file. Okay, so if I open, let me just rename it because we have two zonal statistics layer here, so rename this So buffer, okay. So if I open the attribute table now, okay, I have ID of each point. Okay, so we created 100 points, so we have 100 IDs here, and we have mean temperature of 20 kilometer buffer. Okay, so now we know how an individual is exposed to its immediate neighborhood in terms of the maximum temperature. Okay, so it has a huge research implications. Now it's up to you to form your research questions and utilize these skills. Okay, so I think like you remember like how to export this data. So we need this data ultimately as an Excel file. Okay, so I will click on the zonal statistics, export, and save feature as again as XML file, and I will choose my folder first. I will use here buffer. Okay, and I will click save. Okay, and now we have our data in buffer zones. Okay, so I think I have made my all points here within the time frame, and we have left few minutes for question and answers, and I hope you let me just check within the chat box if you have posed. Okay, before that, let me just finish with the slides. Okay, just a minute. There is one very important slide here. Oops. Just a minute. This is very difficult to. Okay, so let me just go to. So we have seen this. Okay, we how to select UTM zone, and like I want to discuss with you very common errors that you face very commonly when you process raster data or do any kind of geospatial analysis. So the projection choice is very important, as we discussed, like not only for to visualize your maps in a correct position and in correct areas, but also to measure distance. For an example, if you want to calculate land use coverage, okay, within one city or town, for an example, you want to calculate how much area is green, so this data must be into square kilometers, and for that you have to use UTM projections. And to choose the perfect zone, you can always take a reference from the image that I shared. And it is also important to have similar projections of both the layers you use. Okay, so sometimes it works, but it's always good to have have a look of projections of different layers that you are going to use. For an example, our shapefile layers and our raster layers, if sometimes they are they disappears, you have to check about the projections, and you can reproject them. The second thing that is very important is about that we haven't faced this error because the geometry of shape files were already corrected. But sometimes when you when you process raster data with the vector data, it can appear the geometry of your shape file is not correct, and for that you can just go to the search bar of QGIS, and you can write fixed geometries, and you can select your shape file and just hit run, and you will have a new shape file which for which the geometry is correct, and you can avoid this error. And the next thing which is important, there is a user manual which is very useful for those who are using QGIS, and I have given the link here. Okay, so you can check it for each and every tool. They have very detailed description of QGIS, and the most important suggestion from my side, from my experience, I would like to give is don't panic. Okay, the whenever you work with remote sensing and GIS, the errors are very common. You just need to redo things and don't give up. Okay, so this is the set of suggestions that I would give you to avoid errors. And let me just acknowledge first the IUSSP team, Nico, Paul Monet, Mary Ellen, and Sirinji Boy for helping me throughout different stages wherever I got confusion, and also for organizing this event. And big thanks to Valerie Golas, who is a researcher at INED, and we have been doing the brainstorming about environmental data and the problem of scales and analysis since last few months. And the slides you saw here are the results of our combined work. So a big thanks to Valerie and my team members from the Early Career Perspective panel of IUSSP, and of course the enthusiastic participants from various parts of the world. And I see they remain there and interacted well, and yes, maintain the instruction that I gave before. And of course Leo and Basil for extending the help during the webinar. And of course I would like to thank INED for giving all this setup to me. And now let's go to the question answer session for a while. Yes, I can provide you the book references. Maybe I will just list down on the webinar web page few books, and one that I am writing with Valerie that will come next year, maybe next to next year, but it's totally on this topic. I have one question from Molly. Paul, can you unmute Molly? Or okay, you
can
are
unmute.
okay.
Yes.
Okay.
I put it in the chat, and I hope this is not silly, but
yes.
you had shown the site for the gridded population data,
Yes.
and I was wondering if you could maybe speak to how some of that data might be incorporated into an analysis like the one we worked through.
Yes. Like when you download the data, as I demonstrated for each year, we have indicators of 5-year age group. So for an example, if you are downloading that data, you will have a raster file for the country you have selected. Okay, and the pixel value there will tell you about the people per pixel. Okay, so if you want to sum the population of particular area, you can run the same analysis what we did for temperature. But in that case, remember that you will use the parameter as sum, because you want to sum the numbers of people in the analysis. I could not do it here because like every time you download a single layer, it is of 2 GB. So if I have this data during the online webinar, it slow down the speed, and sometimes it doesn't work.
Okay, so just so I'm clear, you would download a layer of the population data you wanted, add it to the environment, and then run the analysis on that layer.
Yes.
And for instance, towards the end, you did a sample of points, and you were saying this could be individuals or hospitals or et cetera, but you could do that same sampling on the gridded population layer.
Of course, yeah.
Okay.
Yeah, just replace your thinking from temperature to people per pixel. Okay, and like you have to remember a few things. As I said, you need to use sum instead of mean, because you have number of people there and you just want to aggregate them. So if you refer to the papers that I presented earlier, one is my own paper where I have calculated district level population for India, and I have described in that publication how this data is extracted. And the other paper very useful for your question could be the mapping the hospital proximity by older age population. They have a good description of that. So I think that would be useful for you.
Thank you.
Thank you, Adi. Yes, Monica.
Okay, thank you very much.
Thank you.
For the workshop. It's a wonderful workshop. I just want to ask, like I'm a demographer, most of my work has focused on health issues. So
Yes.
I'm trying to look at, I'm used to this demographic health service. So for instance, I want to pick a country like Nigeria. They have a very stable demographic health survey over the 5 years.
Yes.
So if I want to merge the demographic health surveys are collected every five years.
Yes.
So now I want to work on 2003 and 2008 and 2013 and then 2018.
Okay.
Surveys together. Yeah. How do I merge it? How do I merge these data together to be enable me to use this QGIS software to work on the data? Probably if I want to look at trends and prevalence of child mortality or trends and prevalence of female gentilation across the country, or maybe across the 6 geopolitical zones of Nigeria. So how do I merge the data? Yeah, I'm a little bit confused. I don't know whether if I will convert the data to Stata format or to Excel, or like as other softwares they usually requires.
Okay.
Thank you, sir.
Okay, Monica, thank you for a very interesting question. And I think this is a very common question for those who use DHS data. So first of all, let me clear on this, DHS data is a cross-sectional data and it's not a longitudinal data. So I think if you use 4 years of data, it would be independent for all 4 years. Okay, so it's not you can't show trends of dynamics of environment or any health indicator because it is a cross-sectional data. And to merge this data, like DHS provides you a shapefile of points. Okay, just like the shapefile we created for random points, you have the shapefile of point data which represents clusters, and they have definition of cluster. For in case in India we have a like 15 to 20 household within one cluster, so it can have a different definition for Nigeria, and you can do the same buffer analysis for any environmental indicators that you want. For an example, there are literature on heat waves and exposure to dots on child birth weights, like child health indicators like stunting and wasting, those things. So I think it's very open question, and it's up to you, like how you see your analysis and what are your objectives. But yes, you can have the geolocations in terms of point shapefile, and you can open that data into QGIS. Okay, and you can merge it with environmental data, and later you can have it in Excel format, and you can open it in Stata or R for your further analysis of further statistical analysis to run any models. I hope it helps. Any other question?
Okay, so if there are no other questions, I think we should close the training workshop, and I would like to thank Ankit and Leo and Basile for this excellent training workshop, and also the early career
That is
panel.
one hand raised. Paul, sorry for disturbance.
Go ahead, go ahead.
Okay, they are just clapping. Sorry.
Okay,
I'm really
that's
sorry.
fine.
Yeah.
Okay, so with that, yeah, thanks to the early career panel. I hope there will be other events organized by this panel, and take care, and don't hesitate, I guess, to contact Ankit if you have
Yes.
difficulties. You have his email.
Yes. Anytime.
Bye-bye. Thank you.
Bye-bye, everyone. Thanks for being here. Thanks, Leo. Thanks,
Congratulations.
Basil. Bye-bye.